what we can do is apply our product and quotient rules in various orders in order to simplify radical expressions. So like we said, we can split apart a radicand into its factors and then create multiple radical expressions with factors that we can take the root of and with factors where we can't. There's a couple different ways in which we can find the factors. However you approach the problem, our goal is to ultimately find the largest factors in which we can take the root. And so we're trying to look for either the largest perfect squares or the largest perfect cubes, whatever our root is. Tried and true method is using a factor tree. And so if we take something like 50 and we want to do prime factorization and we want to break it down into its smallest parts. And so factors of 50 are 2 times 5 times 5. If we're looking for perfect squares, we can identify pairs of numbers that can multiply together to give us a perfect square. So if we have 5 times 5, that gives us 25. So we can break this apart into the square root of 25 times 2. Then using our product rule, we can write it as two separate radicals, square root of 25 times the square root of 2. This allows us to take the square root while leaving the non-perfect squares inside a radical symbol, which simplifies to 5 root 2. Let's take a look at 24. If I want to do factorization of 24, we have 2 and 12, we have 2 and 6, we have 2 and 3, so 24 gives us 2 times 2 times 2 times 3. Since we're taking a cube root, we're looking for 3 sets of numbers, or triplet, that when we multiply together gives us a perfect cube, like 8 times 3. So the cube root of 24 we can split into 8 times 3, the cube root of 8 times the cube root of 3, which then gives us 2 times the cube root of 3, or 2 cube root of 3 as our final answer. If you can identify the perfect square or the perfect cube factors early on in the factoring process, you don't need to do a full factor tree. But sometimes if you get stuck, a full factor tree can help. When we look at 26, and we do a factor tree of 26, we have factors of 2 and 13, both of which are prime. We can't factor these any further. Since neither of these are perfect cubes and I don't have any groups of numbers, this cannot be simplified further. When we look at 4th root of 32, we can factor to 2 and 16. Well, 16 is we can take the 4th root, but we can check by factoring it even further. And we get 4 and 4, 2 and 2, 2 and 2. I have 4 2's. That allows me to take the 4th root. So we can write this as 16 and 2, 4th root. We have the 4th root of 16 times the 4th root of 2, which gives us 2 4th root of 2. 200 has a lot of different perfect square factors. We could factor in a bunch of different ways. We could take 200 and we could factor it into 25 and 8. We could factor 200 into 102. And we want the largest perfect square. Well, this is the factorization that's going to get us there. If we approached it this other way, we would have to take note that 8 can be simplified into 4 and 2, and then I have 2 perfect squares. Well, if I multiply these 2 perfect squares together, I get to the largest perfect square factor of 200. So the square root of 100 times the square root of 2 gives us 10 square root of 2. When we look at variables, we have to consider that the exponent needs to be divisible by the index. Since 2 is not easily divisible by, or 3 is not easily divisible by 2, we need to factor it out a factor that is a perfect square. So the square root of 25, that's no issue. But x to the third, we can break into x squared times x. This allows me to take the square root of x squared, leaving me with just x. So we'll have 2 radicals. The factors that we can take the square root of and the factors that we can't. 25x squared, the square root gives us 5x, and then we're left with square root of x. We're looking for a perfect cube factor of 54. Well, 54, when we apply our prime factorization, gives us 2 and 27. 27 is a perfect cube. So we can factor 54 to be a 27 times 2. 6 is divisible by 3, so x to the 6 is a perfect cube. 8 is not divisible by 3, but if we factor it to be y to the 6th and y squared, I get the largest factor of y to the 8th that is a perfect cube, and then I'm left with y squared extra. So we'll have two radicals. Our first one will be all of our perfect cubes, 27, x to the 6th, y to the 6th, and then the other one will be the non-perfect cubes, 2y squared. So we end up with 3x squared y squared times the cube root of 2y squared. We want to be very careful about paying attention to when we have exponents and indices, making sure that we don't get confused about which is which. If you want to add a little clarity, an optional thing you can do is put this in parentheses to make sure you don't confuse the exponent with the index. 81 is a perfect square, so we don't need to change that. But z to the 11th is not, so we need to factor it to be z to the 10th times z. It means we'll have the square root of 81 z to the 10th times the square root of z, leaving us with 9z to the 5th square root of z. And again, making sure we know that's an exponent and not an index. Now with our quotient rule, we could simplify the square root of 20 and then simplify our fraction. But a lot of times it's easier and a little more expeditious if we go ahead and apply the quotient rule and write it as a single radical with the radicands as our fraction inside. Then simplifying our fraction and then seeing if we can simplify the square root. The same applies for j. 2 is on the outside, so it'll stay on the outside. It's 1/2 the square root, 50x over 2, which simplifies to the square root of 25x. Since I can square root 25, I have 1/2 times the square root of 25 times the square root of x. 1/2 times 5 root x. And then we multiply the factors on the outside, giving me 5/2 the square root of x, or 5 root x over 2. We have our cube root. 7 stays on the outside. Cube root of 48 x to the 4th y to the 8th over 6y squared. 48 divided by 6 is 8. So we have the cube root of 8. X to the 4th has nothing to cancel. Y to the 8th divided by y squared gives us y to the 6th. Now the cube root of 8 I can do. X to the 4th needs to be x to the 3rd times x. Y to the 6th is good for us to go. So our two radicals, 8x to the 3rd, y to the 6th, and then just x. 7 times 2x, y squared, cube root of x, and then we multiply our integers. Here we'll take our 4th root, a2, a8, b6, a to the negative 1, b squared. And we have this 2 out front. 32 has nothing to simplify with. A to the 8th divided by a to the negative 1st is a to the 9th. And then b to the 4th. And then we want to get things we can take the 4th root of. 16 times 2, a to the 8th times a, b to the 4th. Two radicals. 16, a to the 8th, b to the 4th, and 4th root of 2 and a. So we'll have 2 times 2 times a squared times b with our 4th root, and we multiply our integers to simplify our factor, and there we have it.